All right, okay. So, a couple days ago, I was browsing one of my favorite Web 2.0 photo file sharing sites, and it's a special site. It's sort of specialized for Linux nerds. It's specialized for open source software people. It's a knockoff of a common Web 2.0 site. And I'm getting ready to upload my favorite XKCD comic in case somebody else had missed it. And all of a sudden, the site's asking me to fill in, how many shells are in a standard Ubuntu installation. And I'm tired of dealing with this stuff. I'm sure most of you have seen this kind of thing. Have seen CAPTCHAs. They're supposed to prevent automated robots from abusing websites. But, they really, they come in all sorts of shapes and sizes. Some of them are colored, some of them are squiggly, some of them, have grids, some of them are, ask you to solve, high order calculus problems, and some of them don't. But they all really have sort of two attributes in common. They're all kind of annoying, and none of them really work that well. And so what's the inherent problem here? The problem is that in order to make a good CAPTCHA, the CAPTCHA has to be really hard for a computer. But in order to be hard for a computer, it's got to be, pretty hard for a person. But that means that they can't really be too hard. And, this problem allows people to, the niche that they need to break these things. So, in order to talk, before we can really talk about what's involved in breaking a CAPTCHA, we need to talk about when is it worth it to break a CAPTCHA. Like, why do people even bother with this thing? And, the issue is that there tend to be sort of two types of targets involved that are being protected by CAPTCHAs. There are low-value targets and there are high-value targets. And the distinction between these is key to understanding what kind of threat you need to consider. High-value targets, your CAPTCHAs really sort of, they're not really going to do a great job, because if the target is high, if the value of making a post, in the personal section of Craigslist, for example, is 10 cents and it costs 1 or 2 cents to hire a person to solve the CAPTCHA for you, then it doesn't matter about the CAPTCHA. On the other hand, if you have, if you're a spammer and you're trying to spam the entire internet or every blog on the web, then you're much less interested in these high-value CAPTCHAs, and you're much more interested in automating the procedure in such a way that you can hit a huge number of sites, without paying someone 1 cent every single time you post. So this talk is essentially focused on what is involved in breaking a CAPTCHA with automation. And we consider there to be sort of two approaches to doing this. In one case, you can try and attack the back-end implementation of the CAPTCHA generator, and in the other case, you can try and break the actual CAPTCHA problem. You can sort of solve the crux. So we're going to talk a bit about implementation-style attacks first, and then Scott will talk a bit about attacking the actual CAPTCHA problem a bit later. So one of the really common problems in CAPTCHAs and in lousy implementations of CAPTCHAs is that they don't record enough state on the server side in order to tell whether or not the CAPTCHA, whether the solution is legitimate. There's sort of two main classes of state that tend not to be recorded in some cases. In one case, people don't actually tie the CAPTCHA to a specific request. And this is particularly relevant because it means that someone can, say, batch request a large number of CAPTCHAs, solve them very efficiently in a batch mode, and then use those solutions over a long period of time. This is actually a fairly common problem that's present in even some fairly widespread CAPTCHAs. The other problem that's a little bit less common is that some implementations simply can't tell whether or not a CAPTCHA has been used before. And so it's possible to reuse the CAPTCHA several times over the course of usually a certain time period. So here is an example. This is a chunk of code from a defunct software project that's, the software project is defunct, but you can find the code living on in various sites across the web if you look hard enough. And all this is doing is it's comparing the inputted solution here, which is the input solution is string, and it's comparing that to a calculated code. And it calculates the code by taking the MD5 hash of a site-specific key plus the request token plus the state field. but the state field only changes once a day. And so, a spammer can simply solve this CAPTCHA once and then reuse the same solution all day. And this is not an uncommon problem. Another common problem in sort of low-end CAPTCHAs is that the encoding is lousy. For example, the solution of the CAPTCHA is included in a form parameter and, say, ROT13. This is usually done in the name of, the mythical horizontal scalability, because we don't want any server-side state. We don't want to have to remember what the solution is. So we just sort of encode it. I was originally a little bit worried about finding a good example of this problem, but here's something from an actual web page online. It's a reasonable amount of traffic, and you'll notice here the CAPTCHA is asking you to solve a simple arithmetic problem. And there's an x and a y and an operation, but there are three fields in the image URL. There's an x and a y and an L field. And it turns out if you look at it, if you add 12 to the x value in the URL and you subtract 17 from the y value in the URL, then you end up with the actual CAPTCHA operation. And it gets a little bit better. The people who wrote this CAPTCHA were feeling a little bit lazy, and apparently they didn't want to do that themselves on the server side. So they encoded the solution itself in the form. Of course, the solution itself was the MD5 of the solution, and when the solution varies from integers from say 0 to 20, that's not a very large search space. So another fairly common problem is that a single image URL will always return the same letters, but because of again not wanting to retain state on the server side, it will randomize sort of some of the parameters of the image generation. So you end up with lots of different looking versions of the same thing. This is a problem because if you're using an OCR-based attack, then it allows you to very easily sort of pump up the accuracy of your classifier. So we're going to take a quick look at how using some of these attacks looks from a code perspective. Okay, so this is a very simple, basic CAPTCHA implementation, and some very, very basic Python code to talk to it. So first, see, it basically works. If you type in the word correctly, then it lets you through. If you type in the word incorrectly, then it doesn't let you through. But the first implementation has a couple of problems. In particular, this one I think has a static token. It never changes. So this is sort of a basic example of how do you post a request? What's the basic template code for submitting a CAPTCHA solution? So as you can see, it's clearly trivial to break. So upgrading it a little bit, we try and randomize the CAPTCHA solution. But here, if you look at the URL, you see a poorly encoded version of the solution there. If you look at it, any I think right-thinking hacker might take a look at a few letters that they're all ASCII letters, but they're not quite the letters that you see there, and think, well, I don't know what would an engineer do? They'd use ROT13. So let's try that and see what happens. You carefully type that out. Anyway, and so they, your favorite, your social bookmarking site has gotten wise to your attacks, and so they've improved things a bit. And now but now they still allow you to request multiple versions of the same image. Right. So first, we're going to show you sort of a classifier-based attack if you can't request the image more than once. Like, how well does the classifier really work? Just at the baseline level. And you can see it doesn't work very well at all. But taking advantage of this ability to request multiple copies of the same image and using, say, a simple voting algorithm, then you can see that it takes substantially longer, but it works with substantially better accuracy. So moving back to, so these have been sort of some very, very sort of basic run-of-the-mill vulnerabilities that you see in a fair number of places. But let's take a moment to look at some, say, less common vulnerabilities that a little bit more esoteric, but that I think are interesting nonetheless. So one of the key problems in making a CAPTCHA is to generate the code that you're using. And most people, they use some sort of random number generator. Now, we all know that making random number generators that are good is hard, and keeping them that way is sometimes even harder for some people. But, by and large, you'd think that people will be able to do this. But the problem is that most of the people writing basic CAPTCHA packages for web application aren't terribly familiar with this. So they usually fall back on just the basic random number generator provided by their scripting language. So in PHP, they might just be calling rand. Now, admittedly, reconstructing the sequence from just a couple CAPTCHA letters is a little bit tricky, because you're looking at truncated output, sort of a large number indexed into a fairly small number of bits, and then to select whichever character in your character set's being used. And you have to worry about sort of intermediate requests to the random number generator, and you have to worry about, say, multiple servers sitting behind a load balancer. But even if you have to do all of this stuff, you'd really like the security of your implementation to be independent of the actual sort of web server configuration. So just sleep easy, use MD5 combined with the key and the output of random number generator. And just for kicks, let's take a closer look at a CAPTCHA implementation with this problem. So here's a bit of code from a fairly easy to find PHP CAPTCHA. And as you can see, it uses rand, and it simply indexes the output into a character set. So what does the PHP rand function do? Perhaps it does something magic and secure, like you'd expect from PHP. But looking more carefully, you see, no, not really. It tries to choose intelligently between different libc implementations, but that's not really doing so much. I mean, is rand any good? Well, it's a linear congruential generator. It has a couple different implementations. But I think everyone here should know it's bad. But how bad is it really? Like, how many bits of output from rand do you need? How many samples do you need to reconstruct a sequence? And it turns out not that many. For example, if you only have the high order 20 bits, then you still only need 3 samples to do that. And if you only have, say, 5 bits from every generated random number, then you can still reconstruct the sequence perfectly with after roughly 12 to 13 samples, which is sort of well within the range that you can get from most websites' CAPTCHAs. Now, you might think that random is a little bit better if you look to the man page. It says something fancy about a nonlinear additive feedback generator. Maybe that's doing something pretty cool. But this is another one of those cases where then the people who are writing the documentation don't actually know what's going on. If you look at the source, it turns out it's just sort of a linear feedback system, which really means that any individual number is sort of the sum of a couple previous numbers, maybe plus 1. So if you're more interested in looking at this random number generator stuff, here are a couple of references. You can find them on the slides on the CD and on the website. We'll show after the talk. But for now Scott's going to talk a little bit about breaking CAPTCHA using OCRs.
So we're recovering Perl programmers up here, so we're pretty lazy. We like to use other people's stuff wherever possible. Even better if we can use it just completely off the shelf with no work involved at all. So fortunately, there's some really good off-the-shelf OCR packages out there. We have Google to thank for some of that. One of the particularly good ones that we like to use a lot is Tesseract. Essentially, our approach is just going to be to use these OCR engines as a black box. All we really care about is pre-processing the images to make them as suitable as possible for the OCR, and then post-processing the output of the OCR to make sure that we have a sensible solution. For example, a lot of CAPTCHAs are just going to be all lowercase characters or only numbers or something like that. So essentially what we're going to do in the pre-processing stage is make the image from the CAPTCHA as close as possible to typical text that OCR engines like to analyze. So a lot of that's going to involve removing noise, smoothing noise, despeckling, removing a bad background, stuff like that. So we can automate this as much as possible, usually just with a couple of filter stages. It's important to note that this actually isn't adding any data. It's not giving us any more information about the CAPTCHA. It's just making it more suitable for the OCR. So here's a couple of examples of some simple CAPTCHAs with pre-processed and post-processed images. So for the most part, this is just a matter of, like the top example, for example, is a matter of just a thresholding algorithm, right? All we have to really do is drop out the background, and the foreground is all black, so it works perfectly. In the second example, these people think that they've been a little clever by adding some lines to the background. There's not a lot of contrast between the characters and the lines, so that could be difficult. But the lines are really thin, so it's easy to just blur those, get rid of them, and then run the thresholding algorithm on the result. These are pretty easy examples. You wouldn't really see these on a high-profile site, at least not anymore. But we can even handle some pretty higher-level examples, too. So the top image, for example, has also taken the low-contrast approach. They're trying to reduce the contrast between the characters in the background, use some funky colors, run some gradients everywhere, make it a little more complicated. But once again, this is just a matter of an edge-finding algorithm. And then we run the same simple stages. Finally, in the last example, it's starting to get a little harder, right? We have a complicated background. There's hardly any contrast between the foreground letters and the background. And it's not going to be a simple matter of just blurring it. So we can do some complicated tricks here to try to separate the textures if we just use a convolution matrix. This convolution matrix is really optimized for removing that specific texture and that specific scale of image. But really, most CAPTCHAs are going to use similar textures between the background and the foreground across all of the images. So we can pre-optimize the convolution matrix for that CAPTCHA. If you really want to make a secure CAPTCHA, try to use these tricks in all sorts of bizarre combinations and randomize it as much as possible. That means the user has to write a classifier to identify what type of randomization algorithm is being used beforehand. So if we want to improve the quality of the OCRing in general, we can retrain the OCR for a specific character set for that one CAPTCHA. Sometimes this can be really simple. It's just a matter of generating massive amounts of data with like LaTeX or something like that. Sometimes you have to use actual CAPTCHA data. Here's a simple example with the CAPTCHA we saw on the second example of preprocessing. If we take the baseline accuracy of Tesseract with the English training set, we can read the whole CAPTCHA word about 28.5% of the time. And that's with 2,000 samples. If we then crop the character set so that Tesseract has been retrained for just uppercase letters, we can bump that up to 44.2%, which is pretty significant. It's huge for a spammer. And then just to further illustrate the significance of presenting multiple variants of the CAPTCHA, if we vote between multiple OCR results of the same word, we can bump that up to 96%, which is just unrealistic accuracy for trying to defend against. And now Mike is going to talk about some other strategies for cracking audio CAPTCHAs.
So shortly after the first CAPTCHA went out on the web developers realized that, not everyone on the web can see. And everything that's on the web that can't see isn't necessarily a computer. And so there was suddenly a call for accessible CAPTCHAs. And the response to this was audio CAPTCHAs primarily. Now, audio CAPTCHAs, they're reasonably common. You can find them on most high-profile sites. And they offer some advantages to the attacker. In particular, I think there's sort of two primary things. On the one hand, frequency domain filtering of sound is much more intuitive for most people. Most people, you can think about frequency filtering for images, right? And that's, you do a low-pass filter and cut out low frequencies, you end up blurring it. High-pass filtering sort of translates to an edge detection algorithm, but it's not really intuitive. But everyone thinks about frequency-based filtering when they think about audio. And on the other hand, I think that in a lot of senses, there's less room for noise in audio CAPTCHAs. This is primarily due to two things. The first one is that generating speech that sounds good is actually a quite difficult problem. And the other thing is that when people listen to somebody else and they understand what they're saying, a lot of the information about that, a lot of the information that goes into making the decision to classify that kind of information is coming from, say, nonverbal cues and prior context and other information that is not precisely encoded in the audio. And so this means that when you're trying to design an audio CAPTCHA that will be understood by a very wide spectrum of people, you have very little room to add noise that interferes with the segmentation, or to add noise that for example, people would have trouble understanding. So there's very little room for multiple accents and things like that in a useful audio CAPTCHA. And when you combine all of these things, it turns out that in many cases it's not even remotely not that difficult to get decent accuracy on these things. So when you're looking at an audio sample, you generally think about analyzing it in one of two domains. You're either looking at the time domain, in which you just have a bunch of samples sort of moving up and down over time. Or you're looking at it in the frequency domain, where you're looking at the distribution of energy in a particular frequency band. Looking at how bass heavy it is, how treble heavy it is, and all the frequency bands in the middle. So first, let's look at the time domain readout of one particular audio CAPTCHA. Now you look at this CAPTCHA, right? This is just a time domain representation, and you see a bunch of spikes. You see a whole bunch of spikes. Now I wonder where the numbers are in this CAPTCHA. It turns out, if you look at the green arrows, those are all real numbers, and the red arrows are all not quite real numbers. They're all sort of, this noise has been added to try and disrupt an automated classifier. But still, just looking at the peaks and using a simple peak finding algorithm gets you really quite a far way towards looking at this stuff. So we have a short demo of running a simple peak finding algorithm on an actual audio CAPTCHA. I'd like to play. So running this is going to play.
9, 9, 9, 9,
So as you can see, this CAPTCHA I think is encoding 9963 or something to that effect. But what happens is that the peak finding algorithm finds all of the numbers, but it also finds a bunch of noise that's been specifically designed to interfere with the CAPTCHA. But the problem of actually solving that is sort of orthogonal, right? Once you've actually extracted all of the individual number segments, then you're left with the problem of classifying between noise and between the different numbers. Yeah. So right. Okay. So in order to classify these segments, then you need to basically extract a small set of relevant features. Say a vector with maybe somewhere between 10 and maybe 100 or 200 elements that you can use to write your classifier. And on top of that, then you need some sort of classifier algorithm to use that feature data to develop the actual matching set. Now, the thing about it turns out that in speech, almost all of the actual information is encoded in the frequency domain, right? And this should be intuitively clear because people can talk at different speeds and they can talk at different loudness levels, and it more or less still works. People can still understand what you're saying. So in order to, it also sort of turns out that it's possible to, in an efficient way, calculate the frequency content of a sample of audio in efficiently, in a computationally efficient time, using something called the fast Fourier transform. And now the great thing about doing this is that once you've done this, once you've converted your audio to the frequency domain, it becomes really straightforward to do frequency level filtering, to run low-pass filters, to do things like that. And it also becomes, and all that's more intuitive for sound than for image. But one of the issues is that, if you just run a Fourier transform and find the frequency content of every single frame in a short audio clip, then you end up with a huge amount of data, a lot of data. And I actually looked at a couple different feature sets, and it turned out that one of the most effective ways to look at this is something called the power spectral density. And all this is doing is looking at the power of relative frequency, is looking at the amount of energy contained in different frequency bands for over the entire sample length. I'm not going to go into all the details of the math here, but that more or less worked well enough for me. So here's a quick demo of using the power spectral density plus a simple classifier to identify the previously read system. Yeah. So what this is doing is it's running a classifier against all of the little extracted samples, and then using that to figure out sort of which ones are noise and which ones aren't. And it prints out at the end the correct answer, which is 99663. Now, I should comment a little bit about what classifier algorithms I'm using. This is a combination of a support vector machine, or an SVM. Again, I'm not going to go into the math there, but it's sort of it attempts to look at different classes and find, in some sense, the optimal separator, the optimal division between the two classes. And then another algorithm that simply calculates the error between 2 points. The error between the measured thing and the average of the training set. And it combines those to cumulative score, and that works. Yeah. Oh, yeah. How much time do we have left? Okay. So, so I think Scott's going to talk a little bit about another strategy for doing large-scale training of image CAPTCHAs.
So presumably some of you might have been a little upset when we just glossed over actually training an OCR for a specific CAPTCHA. So unfortunately, such an approach is really, really, really time-intensive compared to every other approach we've talked about so far. But sometimes you just have to take that approach. So this is a sheet. This is a sheet of a whole bunch of CAPTCHAs, several thousand samples, and it's identified with what the OCR algorithm using the base English training set thinks each letter is and where it thinks each letter is. As you can see, some of these letters are pretty poorly identified. A lot of them it's split into two. Most of the letters it can't even guess at all. So if we really want to make this accurate, we have to tell the OCR engine when we're training it exactly what each of these letters are and the complete bounding box around each letter so that it can segment it appropriately and extract the right features. Most of the OCR engines don't use a typical SVM classifier or nearest neighbor like we're using for audio CAPTCHAs. They have a completely, not completely, but somewhat different feature extraction approach. So what helps a lot in generating these training sets, the OCR engine is going to expect effectively a data file that summarizes each letter in the training set, where it is in the image, and what it's supposed to be. So if you have to have a human editing these massive training sets, it helps to have a tool to convert back and forth between something that you can easily edit and what the OCR engine actually expects. So among other examples on our website, we'll have a couple of scripts to convert back and forth between an SVG file, which you can easily edit with this Illustrator, and the Tesseract box training file format. So really what we're trying to get at here is that almost every CAPTCHA on the internet right now you can take a reasonable shot at with these techniques. And that includes the best of the best. I mean, even top 5 Alexa sites still have CAPTCHAs that can fall victim to these techniques at some level. For a spammer, it's really enough just to get 2 to 5% accuracy. If you have a huge botnet at your control, then you can throw so many resources at it that it doesn't matter if you have a horrible accuracy rate. So the gist of this is that CAPTCHAs aren't really good for protecting resources to that effect. So there's a couple things that you can do to try to make CAPTCHAs a little bit more significant. The most effective of these is to integrate cultural knowledge. So, for example, a while back there was a hot or not CAPTCHA that asked you to identify hot or not people in an image. And that might be a little more effective, but then you're limiting your user base, right? If you try to ask some Hawaiians what they think is attractive, then it might be different from a set of Australians. So we propose an alternate CAPTCHA, the Bourbon or Scotch CAPTCHA. Wow, I thought we had some funnier jokes in there too. But to that effect, now we're going to open it up for questions. Any particularly good questions will be rewarded, if you're of age, of course, with a shot of bourbon. Or no, we don't have bourbon. Sorry, we have Scotch. Go ahead. Anybody? Nobody. Yeah, that is a very valid concern. So what the question basically was that if you have something that's using a set of cultural images or something like that, it has to draw those images from a database. If that database is of limited size, then the attacker could just completely exhaust all the possibilities and just develop some sort of table to make it easier to pass that classifier. So you have to be careful when developing cultural CAPTCHAs to make it more difficult to do that. So, for example, in a hypothetical Bourbon or Scotch classifier, we might try to add randomness to the image or change the background behind the liquor bottle, or add some distortion, change the shading, something like that. There's a lot of approaches that you can take to try to reduce the attack surface of a database-backed cultural CAPTCHA like that.
Do you think the CAPTCHAs will ever be made obsolete?
Yeah, I think they're already obsolete. It's so absurdly cheap to hire people to break CAPTCHAs, even if you're forced to use a human. The vast majority of resources out there are worth more than the cost of hiring somebody to solve a CAPTCHA. I'm not going to speculate on this, something that grand right here.
I'm happy to speculate. So personally, I think the Turing test is a terrible test, mostly because people are pretty stupid. And it's really, really easy to convince a person that they're talking to another person. That's just my opinion, but anyway. Other questions?
I think CAPTCHAs are best used in conjunction with other techniques, but you really need to be concerned with rate limiting, user moderation, other things like that can try to reduce the effectiveness of spamming or breaking into your resource. But really, you shouldn't expect to rely on a CAPTCHA. All right, well, I guess we're going to... Sorry? It's blended. Johnny Walker Red. Oh, and you guys with the cultural CAPTCHA questions had some pretty good questions. So if you guys want to come up, feel free.
So I think the question was asking what we thought about reCAPTCHA. So reCAPTCHA, by and large, is actually really quite good. I think I haven't looked at their audio stuff carefully, but if I remember right, it has a little bit more noise than the stuff that we looked at. And their image stuff is really quite irritating to segment, even though it doesn't have difficult backgrounds. They do a very good job of making the core problem of running OCR difficult. Their back-end implementation is also sort of quite innovative, in that they use sort of public and private keys to authenticate that a given CAPTCHA is coming from given CAPTCHA solutions from the same site that it was submitted by. But it does have a couple issues. In particular, it's essentially client side in the sense that the client requests a CAPTCHA from the reCAPTCHA servers rather than from their website servers. And one of the side effects of this is that they don't really tie the CAPTCHA to any particular request. And so it turns out that it's possible to implement one of those simple implementation-based attacks, request a large number of CAPTCHAs for a single site, say solve them using a very efficient mechanical Turk interface, and then use those over the course of the next, say, 7 hours. So it's a good CAPTCHA. It has a few issues.
You in the back? Go ahead, real loud. Can't hear you at all. Yell, really yell. Segmentation.
Right. So I think that, right. So I think the question is asking about with audio CAPTCHAs. The segmentation problem turns out to be very simple in current implementations, but there are a lot of things that you can do to make it much harder. For example, you might play a trombone or a music behind a person playing just speaking numbers, and then that makes the analysis much more difficult. So I think that one of the real problems here is that I'm not really convinced that people are good enough at understanding these things that you have a lot of room to do that before the human error rate gets too large and the usability just gets too low. I might be wrong. I haven't done any careful studies about that, but that's sort of my hunch about why you don't see that more often in current implementations, for example, and why it might not end up being a problem. But yeah, certainly if people really started trying to generate conversational speech and things like that, then that becomes very difficult.
It's really sort of unfortunate that we have to worry about all these pesky users. It'd be a lot easier to develop strong CAPTCHAs if we didn't. Yeah, so there are a lot of great text-based CAPTCHAs out there that, for example, ask you to solve math problems or ask you simple cultural questions, but these suffer from the same kind of implementation pitfalls of the other database-backed cultural questions out there. If you have the same math problem that's being presented in the same format every single time, it's a lot easier for a computer to solve that than a human. If you have cultural questions like this, then you have to have a huge set of questions to draw from in order to make it difficult to break. That would probably be the most ideal, but if the spammer can access the same live stream, then you're limited there as well. But good question. That's a great point, and I think that sort of thing can be somewhat more secure, but realistically, spammers have access to a lot more computational resources than your typical web user, especially depending on your type of client. If you're trying to appeal to grandmas with 5-year-old computers, then it'll be a lot easier for a spammer with a huge farm of EC2 instances to break your CAPTCHA than for the grandma.
Yeah, so I'm personally really quite skeptical about using that sort of computational problem to rate limit things like this. Simply because you really end up with this equation saying, well, the more CPU power I have, the more evil I'm allowed to do. And so you drive a very strong incentive, for example, for someone to say, implement your core problem on a bank of FPGAs, for example. At which point they're doing orders of magnitude more evil than the average person and still destroying your site. So I don't think that's a very good solution in the long run.
All right, well, thank you very much.